because I'm going to try to put all the lectures in person and off campus online. All right, so thermodynamics, you can think of it as a theory of energy for macroscopic things. So last semester, we had kinetic energy. What's the formula for kinetic energy, say, of a marble or a point particle? 1/2 mv squared, maybe. We will review that. So that's fine. If you guys ever walk into an ideal point particle, you'll know exactly how to evaluate its energy. But of course, that doesn't happen. And you see something like a table right here. This table is made up of bazillions, tons and tons and tons of atoms and molecules that are bouncing around, and you can't keep track of them. So you're not going to be able to apply the formulas that we used last semester to describe that. So that's kind of in a practical terms, that's what thermodynamics is really about. It's kind of going from idealized point particles that you'll talk about in Physics 1 to the real world. Things like, for example, last semester I told you that Newton's laws describe everything, maybe except for quantum mechanics, but the Newton's laws describe everything in the universe. What about temperature? We didn't use that word last semester. Where's temperature in Newton's laws? So that's the kind of thing that we want to understand. Where does that emerge from? The detailed way that happens is through something called statistical mechanics, which kind of provides the foundation for understanding why thermodynamics actually happens. So thermodynamics is kind of what you see as the bird's eye view. It's the result of, or it is the theory that describes big macroscopic things. Statistical mechanics is what provides the bridge from applying quantum mechanics or Newtonian physics to atoms and molecules, and then how do you get up to a whole table? You have to treat them statistically and understand that. And that's, so for example, temperature is a concept that isn't really useful when you have 1 or 2 atoms. It just doesn't really make a lot of sense to use that. I suppose you could define it, but it's just not useful. But when you get to, well, by the time you get to 100 atoms, then it starts to be useful. If you get to Avogadro's number of atoms, it certainly is a useful concept. So temperature turns out is it's connected to a statistical way of thinking. And that's why last semester we were talking about 1 or 2 things at a time. Well, then it didn't make sense to think about temperature because it just wasn't really a relevant parameter or way to categorize things. Okay, so in this semester, I'm going to be pushing most of those statistical things into YouTube videos, and that's not going to be a push for this course. In past semesters, I've kind of made that part of this course, but because I think we need to get to other things faster, that's where it'll fit this term. That being said, when you get your thermodynamics book, especially when you get to entropy, it kind of is like it's kind of a weird concept that sort of seemingly pops out of nowhere. It's like, where'd that come from? There's really no real understanding. I mean, it works, but where it comes from is harder to understand and has a statistical origin. So I really do think some appreciation for the statistical underpinnings of things makes that conceptually easier. I would encourage you, when we get to that point this semester, I will encourage you to watch the videos to get a flavor of how that works, even if it's not something you're testing. Okay. All right. So through this course, we'll go through, kind of already talked about what the flow of it will be. But the first little bit is kind of trying to sort of connect micro to macro. So how do you go from one atom at a time to large systems? We're not going to do the full thing, but some of that. We'll talk about the first law of thermodynamics, which is energy conservation, the work energy theorem. So it's familiar, but we will have to rewrite it as appropriate for macroscopic things. So it is the same thing, but we're going to rewrite it. Some of you guys mentioned the word heat, for example. We didn't have heat last semester. Well, so we'll have to talk about where that comes from, and it's just there. And then we will talk about thermodynamic processes, so that's how you go from one equilibrium state to another equilibrium state. We'll talk about a little bit about cycles. We'll talk about control volume systems. So at the beginning, we'll talk about closed systems, or sometimes called control mass systems. So these will be systems where basically the stuff you're studying stays right there in a region. It's all accounted for. And then we will talk about control volume systems. That's more like a segment of pipe where you have sort of steady state. Well, you have flow in and flow out. It wouldn't have to be in steady state, but the ones we do will be. So just the way that you think about those is a little different. When doing closed systems or control mass systems, we say control mass because you are accounting for all the mass. You're kind of defining the system by the mass, so all the elements in it. For that, we will use something called internal energy to characterize it. When we get to control volume systems, so that's where you define it by the volume it occupies, not the individual bits of mass. So you're not controlling the mass, you're controlling the volume. Like a pipe segment, then we will use enthalpy more. Okay, so, and when we get there, you'll understand why, but it's the natural thing to do. So that's what we'll do. And we will use entropy in the second law to define efficiencies for devices. And then we'll kind of come back and hopefully finish with really getting into design a cycle, figure it out. You're tasked, you're a mechanical engineer, you're supposed to make a power plant. Run the numbers, tell me what the efficiency of this design is going to be. Or if you want the efficiency to be such a percentage, what temperature do you need to make the water at this point in the pipe? So that's hopefully the kind of thing that you can figure out when we get there. Okay, so those problems at the end tend to be quite large. A lot of looking up numbers in the book, a lot of that kind of stuff, and then just a lot of things happen going in your system. But when you finish the semester, you will understand what's happening in the BPU power plant. It's really not, the understanding of why it is laid out and designed the way it is. That part is not beyond you guys, certainly by the end of this semester. I mean, I'm not saying I could build one because I wouldn't know. I don't know enough about the strength of materials aspect, about what size of pipe has certain strengths, and when does the device fail. But the energy side of it and the power production side of it, that you will understand. Okay, so that's kind of the goal. Are there people in here who want to do chemical engineering? I felt like there were a few of you guys.
You only got about a third of the kids you were talking to last year.
That's half, about 20. So the examples we will mostly use are mechanical engineering type examples. Everything we say, though, works for chemical engineering or chemistry majors. And thermo is the same subject, but what you will find is that different fields use different units. So for example, we will do everything, we will always be thinking about a per mass basis. So we'll do like, how many joules do you get per kilogram or per pound? If you take thermodynamics from a chemist, you probably would do it. What would be the convenient basis there? How do you measure quantities? Do you do it in chemistry? Yeah. If you read a thermodynamics book for chemists, you're probably going to see everything written in a per mole basis. And then you got some stupid unit conversion everywhere. It's not conceptually hard. It's just, you know, you would be better off, rather than using a mass-based set of tables, you'd be faster just to go get a mole-based set of tables and just use a different set of tables for your numbers. In physics, we usually don't do moles and we don't do mass. Usually we do it per particle, so per atom, or per some sort of, or actually per charge is also a common way to do it more. Right? So it amounts to the same thing, but the formulas can look a little different even though it's the same. And so, so we'll have to go through that, and we'll, here at the beginning, we'll do some back and forth conversion from ideal gas law. Does anybody know that? What's the ideal gas law? It smells like roses, right? No, PV equals nRT. Nobody remembers that one? Pivner?
Oh.
Well, but that's actually not how we're going to write it this semester. That one we're going to write it with PV equals nR bar T, because that's a chemistry equation. The engineering one will be PV equals M mass RT. And so then in engineering you'll use R. For chemistry you use R bar, and there's just some stupid conversion between them, but things like that. So we just practice. They're not hard. It's just annoying. Yes.
You do like parts per million.
Yeah. So ultimately, you're doing everything as some sort of a concentration, whether it's a number concentration or a mass concentration. It's a density thing happening. We won't do that here. If you were doing, I would think if you're doing pharmaceutical applications, then yes. So, you know, every field would have their own twist on that. The underlying thermodynamics, though, is the same. Okay. We will just briefly touch on heat transfer. So, we will not really go into different kinds of heat transfer, convection, conduction, I would probably specify them and kind of tell you what they are, but we're not going to spend lots of time on that just because we have enough to cover doing thermodynamics. Usually mechanical engineers take a junior level course on heat transfer. You know, so next year, if you guys are going into mechanical engineering, you would do that, and then you'll be real experts on that. Okay. Questions? Let's kind of over the goal. So, we're going to start with a review. Is that visible on the back? Okay. That's not very visible. All right, so we're going to review a little bit of what we had from Physics 1. So when we started Physics 1, how did we try to describe the world? What was the first thing that we introduced to describe stuff? How did you characterize things? Like, think about Physics 1, first week, or what are the kinds of things we were talking about? Well, yeah, maybe we threw it out there, but we didn't get to that for a couple weeks, yeah. Even before mass. Position, right? We started out just by saying we characterize things by position, time. What else do we have? Position, then we'd also have velocity, acceleration. All right. So let's think about the challenge of trying to apply Newton's laws to describe, this market. Really apply Newton's laws fully to describe what's happening in this market. So last semester, we had position, vector, or R, you can call it whatever it is. But to specify a position in this room, how many numbers do I have to specify? Up, down, right, left, 3, right, X, Y, Z, right? So that requires 3 numbers specified in this room the position of a dot. And then, so I have a particle, say, right here, tip of my finger. And it could be moving, right? So it's conditioned. I ask, what is its state right now? It has a position, but it also has velocity. Right? So you have velocity in the X, Y, and Z. So that's another 3 numbers. So it also had velocity, say for a particle. Those are 3 more numbers. Pull that together, that means you need 6 real numbers. And that's just to say what's happening right now, let alone predicting what's going to happen in the future. That's a different issue. Just to say what's happening now, you have to specify 6 numbers. These are all functions of time, and so you have to do that. You have to study that. What if you had in particles? So what if you had 10 particles? I have 10 particles in my hand, and I want to fully characterize 10 particles right now. How many numbers do I have to specify? 60, right? Because for every single particle, you'd have to specify 3 positions and 3 velocities. So, and then you have 10 of them, so it's a total of 60 numbers. So for in particles, you need 6 in numbers. Why is that a problem? Why is that a problem? Why? Well, let's say you have a handful, a few grains of rice in your hand. How many atoms are in that? That's pretty much a mole, a few grams there. Okay. So, a few grains of rice, that's a mole. How many atoms are in a mole? 6.022 times 10 to the 23rd. Yeah. So this is bad news because if I have a handful, of rice, I'm looking at something like 6 times 10 to the 23 atoms. So how many numbers do I have to specify, roughly, to fully characterize the atoms in the grains of rice?
6 times 10 to the 24.
Yeah, right? I have 6. So this is n. This is the number times that. So I have 3.6. All right, it's a lot, right? So I'm just going to say we need 10 to the 24 numbers to be specified. I'm not talking about saying what's going to happen tomorrow. I'm saying just say what's happening right now. That's how many numbers. Why is that a problem? Well, we can convert it into base 2. But the problem is you would need, I don't even know, we could figure out how many terabyte hard drives you would need just to write the numbers down. When you're talking about, I don't know how many are. I mean, I don't know. I would believe if you were talking about needing 10 to the 10 terabyte hard drives, and you need to instantaneously write those numbers down. We can't do that. I mean, when you have large data sets, like at the Large Hadron Collider, they have these collisions, they have all these particles come out, and as so many particles come out, they can't, one of their challenges is they actually can't, so they measure the positions of these things and their velocities and stuff, but you know, there's another bunch of particles coming just a minute, or not a minute, a second later, split second later. They can't write the numbers to the hard drive fast enough before the next bunch of particles come. And that's fewer than this. So you're screwed. Semester's over, give up, go home, right? So, I mean, this is the key problem with trying to do what we did last semester and really think about every single atom, keep track of every single atom and what they're doing. It's just too many. You can't write that number, you can't write those numbers down even, let alone do a calculation and predict what will happen in the future. It just can't be done. Okay, so this kind of approach isn't going to work. You're going to have to, we're going to have to treat things in a different way. So we are going to kind of not talk about all the details, the microscopic details of the system. We're going to focus in on a few macroscopic quantities, which characterize macroscopic big picture properties that we would use to describe things. So for example, if you think about this table, you know, there's an atom here, and there's an atom here, and quick, look out the window. Does it look any different? No, it's the same table. It looks the same. All of the macroscopic properties are the same. Although when I move my fingers between them, almost certainly some of the atoms probably adhered to my finger and were moved from place to place. So I've swapped, you know, so the table has changed, but none of the essential properties change. So what we're focused on this semester is focusing on these macroscopic properties and the condition of the macroscopic system. We're not going to be following individual bits so much. Okay? Ultimately, you can go from understanding the statistics of those bits to build up properties of the table. We won't do much of that in this class, but you can do that, at least in some simplified systems. You can really do all of that. Okay. So that's kind of the fundamental challenge. And that's what we have to establish here in thermodynamics. We have to get a bridge. How do we go from Newton's laws to a table? because, and it's like really the full table with, right. So in principle, there's nothing wrong with Newton's laws. Problem of practice, we just can't even imagine writing the numbers down. There's so many. That's why we're forced to do this. Okay. Okay, so that's the challenge of the semester. What I want to do next is kind of review energy conservation for a system in like a 1D system. Simplest, the work energy theorem. What is work? What's the idea behind it? And I'm just rehashing the derivation that I provided last semester. I put in the YouTube feed the videos of the work energy theorem from last semester. So just hopefully remind you of that. Don't forget this stuff. You'll use it in dynamics a lot. So so it will come up in other classes. So hold on. There you go. So can you see the top board? Is that okay? Okay, good. One advantage of recording videos in here is that I can have more room than I did when I was doing it at my house. So, even if they push us offline, or online, I'm going to try to do more recording here. Just because I think it's better quality. Okay. Energy conservation. So last semester, we talked about energy. And we talked about momentum, just conservation laws in general. What was the first thing we had to do to use a conservation law? Do you guys remember? First thing you have to do is to define a system. Okay. The work energy theorem works, bad choice of words. It applies always. But to do it usefully, you need to kind of draw a box and define a system, and then break the universe kind of into inside and outside the system. So to use the work energy theorem, and right now I'm really talking about, I'm applying it to point particles like we would have last semester. We will talk about how to rewrite this for more complicated systems. So what you should imagine is, let's say we have a collection, and we have some particles here, or whatever. And we'll put some over here. Should have done a different color. Right? And the first thing we have to do to apply the work energy theorem is to define the system. Visible or not. Defining a system. So everything inside the circle will be my system. And everything not in the system, what will I call that? Well, I don't know, you can give lots of things, but how about environment? So, and the universe would be everything. So we have a kind of an inside and an outside. I thought we would start by kind of writing down the work energy theorem, and then we'll see remind ourselves where it came So what we had was inside the system, there are various types of energy that it could have. So inside the system, we had various kinds of energy. What were the types of energy we talked about inside something could have? Like you could have. Well, we mentioned it today. One of them, I gave you the formula. Kinetic energy, right? Right. You can have a kinetic energy. And then what was the formula for kinetic energy of a point particle? 1/2 mv squared for a point particle. So a particle has a mass, a particle has a velocity. So 1/2 mv squared makes sense to talk about 1/2 mv squared for a particle. So if it has a mass and a velocity, then it has a kinetic energy. It's that simple. So that's inside the system. This is on the inside of it. It has kinetic energy. And now my system here has 3 particles. So how would I find the kinetic energy of this system? What would you do? You just add them up. So it's just 1/2 mv squared, particle 1, 2, and 3, add them up, and that gives you the total kinetic energy. So, what other kind of energy could you have? Potential energy, right? What's the formula for potential energy due to gravity? That's usually what people remember. MGH. Ah, good job. All right, MGH or MGY, right? Height, mass times G times height. So MGY, so the potential energy. So if I have 3 particles and I want to know what's the potential energy for the whole system, I just add them up. We also have, on the inside, we have potential energy. Well, for gravity, the MGY, that's for gravity. You could have potential energy for a spring. That'd be 1/2 K, the spring constant, times the stretch squared. There are different kinds of formulas for that. It's different. You know, there could be nuclear potential energy. There could be, what do you guys have for breakfast? Nothing? If you had breakfast this morning, there could be some sort of chemical potential energy, we're just going to call it, because I don't want to go into the details of molecular. But the point is, you can think about those, these are energies which characterize the system. If I say I've got a Chrysler minivan, such and such make and model, traveling at a certain speed, well, you know its mass, you know its velocity. You can it has a well-defined kinetic energy. So kinetic energy is a property of the system. Potential energy, same thing. Minivan's on the top of a hill, it's on the bottom of the hill. It has a height, it has a mass, it has a potential energy. So potential energy and kinetic energy are properties of the system. Be really careful with my words here. So think of it that way. Think of them that way. Now, can these numbers change? Yeah, right? Cars can speed up or slow down. So its kinetic energy can change. So what we think of it as, it started in one state or one condition before. It ends in another state or condition. So your car breaks down. The engine's broken, so we don't have to worry about the complication of that. Starts out at rest. You and your friend push really hard on it, and it starts to move. Its kinetic energy changed. Did it happen? Is that all that happened? What else was involved in that situation? What allowed for the change, or what caused the change in kinetic energy? cause the change in kinetic energy. What do you and your friend have to do? But you had to push it, right? You had to do something. You had to give it something. You had to give it energy. You had to perform work on it. So what we're going to have, is on the inside of a system, you have kinetic and potential energy. And then kind of from the outside, from the environment, it can go in different ways. You can have some that help and some that hurt. Positive and negative contributions. We have work. And the effect of work acting on the system is to cause changes in energy. So change in of the system. Okay? So if the energy that's inside the system changes, the total energy, then you deduce there must be some work acting on it. So the work energy theorem says work equals the change in the energy of the system. Work energy. All right. How many people remember this a little bit? A little bit? Not much. All right. Just a comment. Did I say, when did I use the prepositional phrase of the system? Of the system. Of system. Didn't use it here. Why didn't I do that?
Because that's the environment. That's the environment.
It involves the environment. It also involves the system, but it's an interaction between them. If I know everything there is to know about a car, in an ideal, 100% of all the details, then I know its energy. It's well defined. But work requires not only that you know where the car is, but you also have to know where Gabe is as he's pushing. You have to know more than just the system. So work is not a property of the system by itself. Work involves the interaction of the system with the environment. The language you use is going to be really important. So you shouldn't think of work as being a property or attribute of something. It really has to do with the interaction with the world outside. Probably seems really simple in this level, but that's going to be a key distinction to make. So that's going to be a big difference. So what we will do, we have this equation, and kind of the power of this equation is, this is a property, everything here is only depends on the system. Two states, before and after. This depends upon how you ran the process, or how you pushed, or the details. And we'll tend to put the things which are system dependent together on one side, and things which are interaction dependent on the other side. We'll do that all semester. And you should kind of think about these things. They're different. They have the same units. Both are joules, whatever, but they're different in the way that they can behave. So that's important. So this is the punchline. I'm gonna derive this now using Newton's laws for point particle, just to remind you where that comes from. It's not. Well, one is it kind of helps remind you what is work, like what's the formula for work, but mostly I'm doing it because it's something you guys should know, and you'll use it in future classes. This is where this is the goal, to get to a statement like that. think their sanitizer stuff they wipe the boards with makes it all smeary and stuff. Won't come clean all the way. Second law. So first off, let's remind ourselves of things. We're going to talk about 1D motion. It's just one particle, one object. Velocity, what's the definition of velocity? Would be change in or D is an E. Derivative, yeah. So it's the derivative of x with respect to b. Okay. And we also have acceleration. What is acceleration? Derivative of velocity, yeah. Which would be, of course, the same thing as the second derivative on position. Okay. Another little kind of cute fact is what is velocity? Sorry, let's go this way. Take the derivative on velocity squared. So that's a product of v times v. So use a product rule or power law. What would it be? Two v. Am I done? dv dt. What did you just change? If this was a derivative with respect to velocity, it would be 2v. But because it's not a derivative with respect to velocity, it's a derivative with respect to time. You have to have the chain rule dictates that you get faster. So that would be the acceleration. That's kind of a curious little thing. Okay. We have that. And aside for a second. Another thing we had last semester was that, so we had forces. What did Newton's second law say? Remember that? F net equals F net equals ma. Yeah, mass times acceleration. Awesome. That's Newton's second law. Now, what we did last semester is that we, it's the net force, it's the sum of the forces, but we kind of segregated the forces into two kinds. We call them conservative and non-conservative. Conservative and non-conservative. So what we did was we said that the net force was the force conservative plus the force non-conservative. I'll remind you what that meant. And so that equals mass times acceleration. And the force, which is conservative, can always be written as minus a derivative with respect to position, not time, on a potential energy function. So this is, it seems random, seems weird. This is what it's defined to be, though. And we showed, you can try for gravity or a spring or any other conservative potential that it works out. For example, let's try to apply this to gravity. So the potential energy due to gravity is mg times y. So I'm going to take a derivative with respect to y, not x. But, okay. So So apply, take minus the derivative on this. What do I get? If I take minus the derivative on this with respect to y, what does this formula tell me? Yeah. You take a derivative, mass is constant, g is constant, derivative doesn't care about them. Take a derivative with respect to y. What do I get? Minus mg. Yeah. So if I take minus the derivative with respect to y on the potential energy due to gravity, I get minus mg. But minus mg is the force of gravity near the Earth's surface. So that's how this works. And every conservative force can be defined in terms of a derivative on a potential. Okay. So what we're going to do is we have Newton's second law with conservative forces, and anything that's not like this, it's just non-conservative. It could be anything. Friction, for example, is non-conservative. Friction cannot be written this way. Okay, so I'm going to rewrite this as non-conservative force equals mass times acceleration minus the conservative force. Even if it's not clear why, I'm certainly allowed to do that. Net force is the sum of all the forces. I can split it however I want. Okay. Now, what we're going to do is, first off, we're going to use this substitution here, which is why this minus sign tells me why I define potential energy to have an extra minus sign, so that the two cancel and they get a plus sign. That's why it is. Say that the non-conservative force is equal to mass times acceleration plus the derivative with respect to x on the potential energy. Just substituting this in there, and the double negative makes it a plus. Okay, so now, what was the little cute trick I suggested before? It might be kind of neat. Okay, this thing. So if I want to use this, I'm not telling you why, but let's say I did want to use this. This has V times A, and over here I just have A. So what do I need to multiply both sides by so that I can use this little identity? Velocity. So I'm going to take this equation, and on both sides I'm going to multiply by velocity. Why? Well, you know how it is. Small town, not much to do. We're in the middle of quarantine and all that, so let's do this. Occupy your mind. So I'm going to multiply both sides by velocity. Mass times V times A, and okay, and there I have 2 VA, so I'll put in a 2 and then I'll divide by a 2. Just doing nothing in a fancy way. So it looks like this. Plus V du dx. Okay, it looks worse. It's getting worse and worse. What am I doing? Gotta get better. Let's make our substitution. 2VA is a time derivative on V squared. So I can say that V times the non-conservative force is mass, actually I'll write this one, is the time derivative on m over 2 v squared does that start to look like? MV squared. Half MV squared. What does that look like? Kinetic energy. Yeah, I'm really just doing algebra to force it into something that looks like kinetic energy. And then we'll just let the chips fall wherever they are. And then over here, I'm going to write the velocity, but I'm going to write it like this, dx dt. Oh, dx dt times du dx. Now, okay, what can you kind of do when you have these fractions, or sorry, not fractions, these derivatives lined up, the differentials lining up like that with one variable? Well, this is just a chain rule. That means that I can just kind of, in my mind, it's like the dx is canceled. Now that's not really true, but it works out as if they cancel like fractions, even though it's not that simple to prove it. So what I can do, write that equation as follows. Write it as dx dt times the force non-conservative. That's this piece, dx dt equals d by dt on this. And then this is really just the same as, so this part is really just the same as du dt. So it's like, it's as if, morally speaking, it's as if the fractions can cancel. That's not vigorous, but none of the mathematicians are in the building, so they can't complain. So, I can write this as d by dt acting on m over 2 v squared plus d by dt acting on u, or a better way to write it is d by dt on the sum kinetic energy plus u. This looks like kinetic energy. This is potential energy. What would you say is the sum of kinetic and potential? Just be the total energy. It's the energy of the system. Right? That's what I remember. The formula I'm working towards is work equals change in the energy of the system. So it's good that that actually appears. This is just the energy of the system. Total energy of the system. All right. So let's remind ourselves, what's the goal? Work is the change in the energy of the system. Here I have a derivative on the energy of the system. How do you go from the derivative of something to the change in the thing? How do you get rid of a derivative? Integrate with respect to time. Integrate both sides of this equation with respect to time. The derivative goes away, and fundamental theorem of integral calculus says the integral of a total derivative is the difference of the thing being differentiated, evaluated at the upper and lower levels. It's the change in energy. We're going to integrate both sides with respect to time. And then this is going to give me the change in the energy. What was the goal? Work equals change in energy. change in energy equals all this crap. You know how we can fix this? We just give this a new name. We call it work. That is, this is work. So we learn, so this is the derivation of that formula. And what we learn is that the work is the integral, and I focused on the non-conservative forces. I didn't have to split it that way. Remember, you could choose the system differently. We had that last semester. Maybe you use potential energy, maybe you don't. Okay. But in general, the work due to a force, this is true, or, so this is an integral dt. Don't forget that. Or you can, again, pretend they're like fractions. This becomes the integral of the force over a distance. This is integral integrated over time. So using the chain rule, change that into an integral over space. Work due to a force is the integral of that force. Yes. And you integrate from start to the end. That's the work energy thing. So notice, well, it depends on the path you take. You go from A to B, you go through different paths, you can get different amounts of work, like that. So it's not a property of the system. Okay, so I'm a little behind what I wanted to do for today. So we're going to do some examples next class evaluating this for a few things. And then we will, but mostly next class, we're going to work from this point particle stuff and start introducing fluid property, density, volume. And we'll use those ideas to define pressure. And then we'll talk about how you evaluate work in the context of a fluid instead. So you have to kind of, it's basically this, but you have to tweak it and adjust it for that context. So that'll be the goal for next class. Okay, out there. So, Sapon, we'll see you next time.